Right. We next move on to solving congruence class equations. So let m be a fixed positive integer, and we want to solve this equation ax equals c for two given integers a and c. We want to find the congruence class x which will satisfy this equation. So since we are working with in the ZM class, the set here, we know that the solution has to be one of these. So that's the good thing. This is finite mathematics, this is modular mathematics. Unlike the earlier examples, here we know that the solution has to come in this class, so that there are maximum only m possible cases that we have solutions for. So for example, let m be equal to 7, and if I want to solve this congruence class equation 5x equals -4, I can use trial and error because I know there are only 7 possible solutions for x maximum, so I can just use exhaustive method and plug them in, and you will very soon find that x equals 2 is the solution, and therefore you have that. And whether that solution is unique or not, we will discuss. There may be other solutions, but for us one solution we have x equals 2. And because 5 times 2 is 10, and 10 is related to -4, because 10 plus 4 is 14 and gets divided by 7. But in general, if you want to solve ax equals c, if m is a large number, then we can't use this exhaustive method. It will take too long. We need other methods. So if I want to solve ax equals c, and that's equivalent to solving, if I can multiply ax has to be related to c through the modulo n, because ax has to be related to c, because that's what the equivalence classes are. So we are solving this equation ax equal to c. That means ax, I'm sorry I missed that. That means ax has minus c has to be some my for some integer y. It has to be a multiple of m, so my. And then if I bring that over, you will see this is kind of a familiar equation. It's a Diophantine equation. So that means solving this congruence class equation is essentially solving a Diophantine equation with two variables x and y, and we can solve that. We learned earlier to solve Diophantine equations, we need to know whether there are solutions. There are solutions only if a and m, the greatest common divisor of a and m is d, and that divides c. So if that d divides c, then we have solutions. If the d doesn't divide c, then no solutions to the Diophantine equation. That means no solutions to the congruence class equation. We can solve these congruence class equations easily by using this very nice theorem which makes things so easy for us. So let m be a fixed positive integer, then the equation ax equals c in congruence class modulo m has solutions only if d divides c, where d is the greatest common divisor of a and m. So if d divides c, we have solutions, otherwise we don't have. And it's not only that, this d also tells us the number of distinct solutions. So moreover, there are d number of distinct congruence class solutions given by that, where x0 is one particular solution. So if you can find one solution, then we can write all the solutions, because there will be a d number of solutions. If I can find one, I can then generate the other solutions, and all the solutions are given by this. And we can write the complete solution set for a particular solution. If you know x0, then x0 plus m over d, 2m over d, and so on goes up to that. So there are d number of solutions here. D number of solutions. So this theorem is very powerful and it's very easy to use to solve a congruence class equation. Just look for D. If D divides C, we have solutions. You have to find one solution. To find one solution, the first solution, we can use Euclid's extended algorithm and find one solution. Once you find one solution, we can then generate the other solutions. So these congruence class equations are nothing other than Diophantine equations, just written differently. So solving congruence class equations, very simple. Suppose we are asked to solve this and we are told that m is 6, and to solve this we know a is equal to 3, c is equal to 5, m is equal to 6. First thing you want to do is to see whether there are solutions. So let's look for D. D is equal to 3, but 3 does not divide 5. So immediately we know, okay, there are no solutions, we are good to go. So that's easy. Let's look at this equation. Second example, suppose 4x equals 6 and m is 10. We do the same things. A is 4, c is 6, m is 10. Now D, when we check for solutions for a and m, the greatest common divisor of a and m, that's equal to 4, because 4 and 10 have GCD of 2. So that's 2. So now we do have solutions because D divides C, so we have solutions. That means we'll have two solutions, because if there are solutions, there will be a D number of solutions. So there are D number of solutions, so we will have two solutions. Now in this case we can be lazy and cheat, because m is a small number, it's only up to so 0, the possible solutions are 0, 1 to 9, because we are in congruence classes, modulo 10, so only up to 9, so you can just use trial and error and you will find that 4 and 9 are the two solutions. And you plug that in and you can check your solutions. If I use 4, so 4 times 4 is 16, and 16 is congruent modulo 6, so 4 is good, and 9 as well. 4 times 9 is 36, and that's also congruent modulo 6. So therefore our two solutions are 4 and 9. We already saw that there are two solutions. The situation gets a little bit harder if you have a large m. So let's look at our third example with a bigger m.